Hi and welcome to a new test and teardown video.
Thank you very much. Here we go. I get some real fun stuff in sometimes. Look at this really big meter here. It looks like it has been some sort of a reference measurement system or of some sort. I see some painted numbers down here, so I guess there were like a lot of cables screwed into here, right? See a little resistor, probably some tests, something. And so I guess this is how you select the different inputs. And this switch is just huge. Let me get some light here. I mean, look at this. This is super good feeling about this selector switch. And then there is a 0 and a K. I think that maybe the idea is K is for calibration, so probably use 0 or a calibrate to, probably that is the K, right? So if you put it for K and then you adjust for this value and then you put it for 0 and then you check, this is your 0, right? But then it's 0 is in the middle here as well. So it's plus minus 10 Celsius. I really don't know what to expect. It is like really big and nice, this wooden case. There's also a lid and there's no text written anywhere. And this lid can lock in place. So it looks like it was some sort of an important kind of equipment. The case is quite nice too. It could use a little bit of sanding and a new layer of new varnish, so it will be nice and new. So I can't do a lot from here. I think we need to unscrew it. All I did was to clean it up real nice, so it's super nice and clean. This the meter here is a Bakelite, and look at the size. What is it? Almost 19 centimeters wide and what, 17 height. Wow, that is some meter. And I also checked, see if I move it like that, there is exactly the correct feeling. So it looks like it's working. So yeah, let's unscrew and see what's inside. I hope there's no battery inside. I was not that wrong when I assumed something about a battery inside. Look at that. I mean, that is definitely a big battery holder, right? And those two, one is marked red. So I guess there were like a very big battery in here, and it's also done some battery acid damage right there. So luckily there's no battery in it. And so the two battery wires, they go down to that area here. And again, marked red. And we got some reference resistors of some sort, and they wrote some values on those resistors. Oh, wow, that looks very wild. So what exactly is that? Oy, 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 this is old. And then there's a really funny connection here, but okay, so all the wires to the outside terminals, that goes in here, right? And remember the switch, it's a 2-decked switch with a make before break kind of switch. I don't know if that is intentional. And one deck here, all the connections, they're just connected together, all the outputs of that switch, and then there is a wire down to the bottom part as well. So I put the switch here in 0, and that means it disconnects at both ends, so that will be power off. So that will be 0. If I put it into K, that is the first, and then it connects on both of them. Probably for calibrate, I don't know. So my idea is I'm going to put it into K position and put a variable DC supply here and see if there's anything going on. Probably, we probably need to connect something on the terminals here, and probably there will be voltage on the meter. There's also a 100 ohm pot. So yeah, we got some very low. Aha, that's also 100. That is interesting. What about that resistor down there? That looks a little bit. Ay, ay, ay. I mean, how old is this thing? This kind of switch here is really, really good, by the way. They look old and funny, but the way they were made with this contact kind of system, that is the good old type. And all those 3 blades here, they are flexible and individually like digging their way into the metal on each end. And this is a known very, very good way to do this. And there's a very low resistance, constantly good contact in this type of switch. As you can see here, it's just digging its way into the metal. And the more you use this, the better they just become. So still very, very good feeling. All you need to do is add a drop of oil to that wheel, and then it's gonna be super smooth again. So that is what I want to do. But hey, let's see if we can figure out what this probably is. Some sort of an ohm meter. Oh, there's a red resistor down there. So there's a resistor in series with that pot meter. And then where's this wire going? It's also a little bit stupid. All wires, they're the same color, but I think we're going to figure this out quite fast. What do you know? 4.5 volts, obviously. That's 3 elements. And then I put it into K, and I think this pot is about, yeah, that is quite funny. It is about center position. Then I can adjust. Yes, it is. Then I can adjust K to that position. And the current consumption is 18 milliamps. Is it going? Yeah, okay, it is 15 milliamps. Okay, so that's quite cool. So that is the calibration, I guess. And if I dial it down to 0, then there is no current consumption anymore. So that is definitely how it works. Let's. Oi, oi, oi! Did you see that? It just hammered. Okay, so that is weird. Why would it do that? Bam! That is weird. So we need something with very low resistance to ground or something. I did not expect that to happen. Look at that. But okay, that is not what I expected. This is 18 milliamps, all right? And when I dial to 1, the meter hammers up and current consumption is 14. Well, that's interesting. Okay. This is really funny. I've actually figured this out now. So every sensor, you need 2 wires for each sensor. It says like here 1, 2, 3, and so on, right? So I screwed in these wires here. So this cable goes to this resistor box. So to get this in 0, there's actually a bridge in here. So that means if it's open or if it's shorted, it hammers to both sides. So to have this in 0, we need 99.6 ohms in here plus this cable. So that's probably 100 exactly on the terminals here. It's that accurate to give it a 0 here. And what I did is, of course, I put it into K for calibration, and then I adjust it to that point. So this is actually an ohm meter, but I would assume that the sensors, they change their resistance exactly this much. Hey, how about we find out? So if this is 100 ohms, that's like very accurately. So if I dial it up 1 ohm, that will be this one, right? And it is on 9. Oops, I dial it down then. So this is 1 ohm. 1, 2, 3, 4. Okay, so plus minus 4 ohms from 100. That is the range of this meter. So this is how it works. So you can see here, if I try and dial open, see, and it hammers up. So that is how it is. It's an ohm meter, but it's a bridge kind of setup, and 100 ohms is 0. Well. Maybe we should figure out what kind of sensor that is. That is a little bit interesting to make it read Celsius. That was almost too easy. Of course, it's a 100 ohm platinum RTD temperature sensor. So look at this, what I found here, a resistance versus temperature table. So here's how it works. At 0 Celsius, the resistance is 100 ohms. All right. So if the temperature is minus 10 or plus 10, it's about 4 ohms difference. So all we have to do is put in a 100 ohm RTD, and then we'll have a temperature meter here that works. How cool is that? It turns out there are quite a lot of different types of RTDs. You can of course see here the annealed copper, platinum, and silver. They are very close to 4 ohms for a 10 Celsius change, and that means they could all 3 of them be used with this meter. I will put a link to this page in the description so you can have a little look about RTDs.